Hi, and welcome to Codex. Today, our speaker is Professor Philipp Petersen. He earned his bachelor's, master's, and PhD from the Technical University of Berlin. His dissertation was awarded 2 prizes, one from the International Association of Applied Mathematics and Mechanics, and one from the Berlin International Graduate School in Model and Simulation-Based Research. He held 2 postdoctoral positions, first in the funded research group Discretization in Geometry and Dynamics, and then at the Mathematical Institute of the University of Oxford. He's been assistant professor at the University of Vienna for 1 year. Professor Petersen is also one of the organizers of the online One World seminar series on the mathematics machine learning, which I encourage you to check out. On a more lighthearted note, while still a student, Professor Petersen created a number of hilarious applied harmonic analysis memes. His research fields include approximation theory and structural properties of neural networks, applications of deep learning and numerical analysis, and applied harmonic analysis, in particular multi-scale systems. These areas will all be touched on in his talk entitled Functions with Structured Singularities, Completely Harmless or the Biggest Challenge to Computational Math Since Traveling Salespeople. And take it away.
Thank you very much for the introduction. Thanks also for pointing out that I'm very skilled at creating memes. It's one of my biggest accomplishments. So Emily started. So this is probably the only time that I will give this talk. So usually people give talks multiple times. This is definitely the only time I will give this talk, I think, because Emily sent me an email as the invitation, and it says, "Don't talk about what you usually talk about." I'm paraphrasing slightly, but kind of along those lines. So that's why I talk about functions with structured singularities, and this is basically a story through what I did in my PhD to what I'm doing now. Yes, so these are the kinds of things that I'm talking about. I have this highlighter. These kind of functions, yeah, I want to work with. So I have a certain domain. Yeah, it can be 2D, like in this picture, but it can also be anything else. But it was just easiest to draw in 2D. And then these functions, they are usually smooth. So in this picture, they are piecewise constant, except for one special area, and there they have a jump. And this jump also has a kind of regularity. And I'm kind of, the main theme here is how well I can approximate, represent, or work with this function, influenced by the fact that it's not continuous, or is it only influenced by how smooth this curve is, or what I know about this curve. And I hope in the end we will agree that only the smoothness of this curve is really important and not the fact that it is discontinuous. Okay. These things appear all over the place. So of course, what I did in my PhD, and I think it's also a frequent topic in this seminar, is image processing. There, we were told to believe that images are piecewise smooth functions, maybe with some texture. So especially they're piecewise smooth, so they can have jumps along curves, like for instance this butterfly here. And then there's texture, which we can maybe forget about for now. So this is a good model. But also in classification, like as people doing machine learning, here's a typical example of this iris data set. So these are every point here represents a special one data point of a flower, and these here are 3 pictures corresponding to 3 classes. For me, it's very hard to distinguish between those, but if you know 3 properties of them, no 4, then you can make this classification. You can make a classification. In fact, in this case, we only use 2 properties of those. And okay, this is generated by nearest neighbors, but you can do more reasonable. You can draw more involved or advanced classifications. The point is this in the end is some sort of a function, and it takes 3 values because these are 3 different types. And yeah, again, I mean, you can ask yourself, is this a smooth transition or not, and what does it mean for algorithms? And then also in PDEs, more applied areas, not to say that these are not applied areas, you also have these kinds of functions appearing. So this is an example here of 2 material, like oil and water, let's say, and they were mixed, and then you have an evolution over time. So this is a Cahn-Hilliard equation, and with time they will separate. And the interfaces between these 2 things, they will be in some sense smooth. And if I want to model this, let's say if I want to solve a variational problem, then I have to make an ansatz for these solutions, and then I want to represent again functions with singularities along structure. And the last picture down here, this is from something from fracture evolution. So someone is ripping apart a piece of paper. The piece of paper is basically a function, modeled as a function with a jump along where I ripped it apart. And again, you know that this curve has a certain regularity, depending on how you, of course, pull on the paper. Okay, so here these things appear, and I want to just make a bit more mathematical formulation, which isn't yet very precise. So these functions will always be of this form. Yeah, so I have a function f that I can write with these 3 terms. f1 and f2 are both some functions, and they have some regularity, and I will specify this. We will have lots of examples, but you can think of differentiable or Sobolev regular with wk infinity or Bezov, you name it. And then the second ingredient is this characteristic function, and this is characteristic function of a set B. And the only thing I want to really assume about B is that the boundary has some certain regularity. So it could also be, let's say, Lipschitz, for example, could be better than that. So these are the kinds of functions that I'm looking at. And then, of course, the task that I have, and this is still reasonably vague, is I want to work with them. So I kind of want to approximate them or want to represent these functions or anything along those lines. So I fix a certain regularity. As I said before, we'll have some examples for these FIs and for the boundary curve. And then I want to find a parametrized family. So these are functions. They're indexed by some parameter. Here it's theta in some family large theta. And this should be so that each of these functions f can be quite well approximated with one element from that family. Okay. And how to find such a parametrized family, and what is a good, what would be a good one, and what do I mean by small? That is hopefully what's next. So we start by basically the only example that I knew during my PhD, which was this cartoon-like model. So people say this is due to Donahoe, even though he has never used this word, I think, in any of his papers, but the definition appears. And so these are 2-dimensional functions. Okay, so here for reasons that will become clear in a second, I assume that they are defined on a cube, and they're C2. So these FIs are C2. And then I have a boundary curve, and that is also C2. And so assuming that, well, F2 is not 0 on this jump curve, this is not a continuous function. And so it's reasonably easy to see that if I take the discrete Fourier transform of it, that will not be in the sequence will not be in L1, small L1. Otherwise, this would be continuous. So from that, I mean, it's clear that it's not so easy to represent these functions with complex exponentials. Yeah, so functions of the form e to the minus 2 pi I, and then I have a k and an x here. And represent in the sense that, well, I just need very few of them to approximate f. So if I look at this thing here, for example, so this is the this is a set where there are only n entries in. So it's an n-term approximation with respect to complex exponentials. Well, then, I mean, there's a well-known formalism how I can relate such a statement here, basically via Parsifal's identity, to the decay of the coefficients. These are the CJs. So if they're not an L1, something that's called Stechkin's estimate, you guys all know this because this is basically the what's done in this seminar all the time, then you get obviously a lower bound and this n to the minus 1/4. And so you could say, well, in this case, this is not really that great, even though at this moment we don't even know what is the best way to do it. But let me just tell you, n to the minus 1/4 is not so great. And then people have been thinking about this more because, okay, this is an interesting class of functions. And then, of course, they came up with these other things like wavelets, shearlets, and curvelets. So I will just go through this very briefly, even though probably kind of the core area of this seminar. So for wavelets, and wavelets are these isotropically scaled functions. So you have a couple of generator functions. So typically these are generated some sort of tensor product. This will become vaguely important later. So one direction it is it has vanishing moments, in the other direction it may or may not. And then the wavelet base is just constructed by isotropically scaling these elements and shifting them. And in the end, it's going to be a basis. Now, if I want to represent this function with a jump along a curve, well, because this is an orthonormal basis, again, Parsifal's identity tells me that, well, I kind of need to look at how fast the scalar products between these basis elements and this function decays. And well, it turns out it doesn't decay that quickly because there are actually quite a lot of these individual wavelets that intersect this jump. And if a function has a vanishing moment and lies on something that has a jump, then this is not going to decay as quickly as when it lies on something where it is smooth. So because of this, you'll have somewhat slow decay of the coefficients. You can put all of this together and shake it a little bit, and then you get a lower bound on the approximation rate. That would be n to the minus 1/2. Okay, so you could say maybe this is actually good, but from what we just discussed, I mean, we kind of had the impression that the problem is that I need to cover this whole line. And so maybe if I can be a bit smarter and don't cover the whole line, but use things that are a bit longer, then maybe I can have a more efficient approximation. Okay, so here I cleverly, without telling you, switched from estimating scalar products and asking how many do intersect the curve to how many I use to cover it, which is not necessarily the same. But let's not go into that tangent. So with these functions, so the functions that are now elongated, and maybe I can also shift and rotate them. So these things are curvelets and shearlets. I can get actually approximation of function like this, and that rate of this is n to the minus 1. That's twice that of the wavelet basis. So it's actually could be quite nice. Let's see. Well, it turns out this is actually quite nice. So there's this optimality result. If f is C2, if the boundary is C2, then no dictionary can get us a better rate than curvelets or shearlets. And this rate is n to the minus 1. So there's a small technical condition, which is of course very important, which is that in searching for this n-term approximation, I'm not allowed to look through the whole dictionary. So I can only look through the first n to some power elements. Yeah, and so for me, this theorem was almost kind of the standard to what I want to reach when I build some approximation of functions. And it's actually, so in hindsight, it's kind of embarrassing, but I really never asked myself the question, why C2? Yeah, and actually, I'm convinced that the only reason one chooses C2 here is because otherwise, either shearlets and curvelets don't get this rate, or it's not optimal. Which, I mean, so we can ask, what happens if we change something about the regularity here? And so here's basically the idea. So if so what we're kind of doing is we have these functions, these singularities. We're trying to resolve them with a system. And if I use this covering by wavelets, it's basically, well, if I look at the Taylor representation of this curve, then I'm not using any information of the slope or anything. It's basically a 0th order adaptation to it. So I just know at which point, basically, I want to put the next wavelet. And then with the shearlets and so on and so forth, I can basically adapt to at least the slope of this thing. And so nobody tells me that I have to stop here. I could go further and really fully resolve whatever I can. Yeah, if this is a smooth function, I can bend and do whatever to my elements, and I should get actually better approximation. So, of course, this assumes if I think in terms of Taylor, then this assumes if I do first order adaptation to measure the error, then I need 2 derivatives. And if I do kth order adaptation, I need k plus 1 continuous derivatives. And in fact, this has also been done. Yeah, so there's this paper, Surflets, which I think is fantastic, but I don't know if so many people know it, which does exactly this, and actually in arbitrary dimensions. So, and gives us an approximation rate of functions which have smooth curves, k plus 1 derivatives of these jump curves, and then the rate is n to the minus k plus 1 divided by 2d minus 1. So if I put here k plus 1 equal to 2, like for cartoon functions, and d equal to 2, then it's exactly, hopefully 1. Yeah, then this is exactly 1. So this is the rate that we also had for shearlets and curvelets. But if I improve the regularity, then this tells me I can also do much better. Something that curvelets and shearlets don't see. And so from here, I can ask myself, am I, so let's just very briefly say how this works. So they basically they follow this idea. So you know the Taylor, if you know a Taylor representation of the curve, you can specifically design your dictionary just fitting this curve. Now, that's not such a universal system. So I'm thinking, can I have something that's not so adapted to this problem, especially also not necessarily to the specific k, and I don't have to build it for every function. And so of course, yeah, so it's not going to be a surprise. I come up with neural networks at this point. My claim is I can get exactly the same rates. We'll see if I can do even better if I use instead a neural network and no specific adaptation to the function or the k, even though this there's a small asterisk here. So I will not exactly do this for all k, but only for a range of k. Okay, so before we do this, I need to define a little bit what I mean by neural network. I mean, most people probably know this, but of course we need to fix the notation. So for me, this is a function. It maps from RD to RNL, but RNL is in this talk always 1. So this is the number of neurons in the Lth layer. So D is the input dimension. L is the number of layers. I have an activation function, which I call rho, and it's almost always going to be this one, ReLU. And then I have a fine linear maps. TL, is how they're called. They map from NL-1 to NL, RNL. So these are the numbers of neurons in these layers, like here. And they're fine linear. And then the network is built like here. So it's a composition of the first defined linear transform, then component-wise, coordinate-wise, the activation function, and you proceed like this, L times, and that's the function. Okay, so here we have our first result. Let's say I have, again, this set B, it's d-dimensional. F is of this form. These Fi's, they are k times differentiable. The boundary curve is k times differentiable. So this is the setup that also the servlet had. Then I can have a neural network. It has m weights, and when I say weights, I mean the number of active parameters. So these are the number of non-zero entries of these affine linear maps. So in a affine linear map, like here, this is, you can of course write as a matrix in a shift, and then I count the number of non-zeros in there. And this, that's m. So for all L together, that's m. And so here I get this rate, which is precisely the one that we get for the servlets. And I need a certain number of layers to achieve this rate, and it's k divided by d. So there's some adaptation to the smoothness of the curve, but I mean, it does also work, I mean, for all values smaller than a certain k. So I can do with rougher curves, and then I will automatically just be a little bit worse, but I don't have to change my whole method. Okay, so how does this work? Let me just prove this. So the proof is basically 3 steps. So I have this function here, and then first I have some kind of a localization step, which right now I'm not talking about because I will do a similar proof later where I will show you how to do that. But let's say I can localize, and I can localize this function to get something like this. And this I would call a horizon function, because in this representation, this is a function, and this is a smooth function. So it's a function. I can write locally the this function here in this form. Okay, here maybe I have to relabel the coordinates. Yeah, but apart from this, I can locally write like this, and the regularity of this gamma function, which is the function along which I have the jump, that's the same as the regularity of the boundary curve earlier. And actually, it's easy. You can write this thing also in terms of a heaviside function, which I now call h, of this here minus x1. Now, the heaviside function is not hard to build with a neural network. In fact, there's a fairly standard construction. So if the activation function is this ReLU, like the ramp, then I just subtract a slightly shifted ramp, and then I have almost already the heaviside. Just maybe need to rescale this slightly, and then you approximate this well. And then the second thing is I need to build this gamma. Okay, then the gamma is a CK regular function, and I'm claiming that this is kind of classical neural network approximation. So classically smooth functions is not so hard to approximate. That is, of course, a massive stretch. In fact, took us like 30 pages to prove this, but the idea is standard. So you rebuild polynomials and use classical polynomial approximation to approximate these functions. Also for us, it was only hard because what we want is here a bounded number of layers, and it's a standard, but also a 3 or 4 year old result to do this with an infinite number of layers, growing number of layers. So we wanted to have something bounded, and so that makes things a bit more complicated. But so let's not worry about this one. The other parts are actually fairly simple, yeah, and it's really, we can build this just basically because of the compositional structure of networks. You know, we can compose the heaviside with something smooth, and that's how we can build all these horizon functions. Okay. Oh, no. So now I said at the beginning, okay, this regularity that we had for for the cartoon class was C2, and I think that's arbitrary. And so I just generalized to CK. So I have to accept also the question isn't like CK arbitrary. And it kind of is, yeah. So really don't need to make this assumption, and to show that this is not necessary, I'm just going to show how you can get the same result with a different function class. And I think when you see the next result, you'll probably say, well, of course this holds. Yes, it's kind of obvious. But I think the implication of it is actually quite amazing. But we'll see what you think. So here's this kind of, I would say, celebrated function class of Barron. To these functions f that you can write as, well, okay, this is just the representation of f by the inverse Fourier transform, of course. So f hat is the Fourier transform. And I want that f hat has a certain property, and that's that it has a moment, and I call this CF. And now all the functions that, well, where their Fourier moment is smaller than a certain c, I put them in this function class gamma c. And so this is the Barron class. And there is this quite famous result. So if you have a function of this Barron regularity, so let's say f, then on a ball, and mu is a probability measure on that ball, I can approximate f with a neural network fn. This has 2 layers, so it's a shallow network, and it has n neurons. And I have an error that is this. So it's basically this, well, this Fourier moment, and I divide by square root of n. And at first you would say, okay, this is quite a bad rate. We've seen this before. And you told us that, well, n to the minus 1/2 is not such a great thing. But the amazing thing about this statement is that this ball has a certain dimension, and this dimension doesn't appear anywhere else. So it's the approximation rate is independent of the dimension, which is kind of, yeah. So depending on who you ask, this is either completely groundbreaking or not so interesting. So if you read, or if you have read at some point the dissertation of Emmanuel Candes, which I think everyone should do at least once because it's kind of funny, he talks about this space a lot. And he actually says that he's not as impressed by this result. I don't know, hopefully not in the audience right now, but neither Andrew Barron nor Emmanuel Candes. But so Candes says he's not that surprised of the result because even a Fourier, like complex exponential approximation, would get this rate. So it's not really something so special about neural networks if you can do the same with just standard Fourier techniques. Okay, more on that maybe later. You can actually even generalize this, and that's kind of a neat result, to an L infinity estimate. And this is the one that we will use later. Okay, so in fact, this space is like been studied a lot recently. So by E, Ma, Wojtowicz, and Wu, for example, but they have a lot of papers on this, on generalizations of this Barron space. And basically what the construction there is functions are in this Barron space, in this generalized Barron space, if they can be represented like this. So if I can write them as an integral, and so this is the ReLU with respect to some probability measure. So basically, if I can write them as an integral over just one neuron, and the weights can be chosen according to some probability density. And if I can do it in this form, and well, there's a certain norm of these measures involved, then I would say f is in this generalized Barron space. As the rho is, again, just to indicate that it's different, and the c, that's this constant that comes here from the measure. And if a function is in this generalized Barron space, then again, you have the same rate as for the classical Barron space. You can approximate here, and the error is 1 over square root of n, and there's no dependence on the dimension. And so we were quite surprised when we saw this, because this is advertised as a generalization of the Barron space. And in fact, when you look at this closely, you find out, and I don't know, for some reason this must have escaped people, that this is not at all a generalization. So actually, the classical Barron space is not a subset of this. Under some additional assumptions, it is, but in general not. And in fact, you can easily see this, but I don't know if I want to do this right. Yeah, maybe I want to do this. So basically, if you just look at this representation from before, yeah, f can be written like here. And this is the ReLU. Then I can just take the derivative of f, and I just can pull the derivative in. And obviously, the derivative of the ReLU is the Heaviside function. And then, okay, I have to use the chain rule, get one of these w's out. So basically, I know that the derivative is of this form. And now if I look at this closely, I mean, these are lots of jumps, and I'm integrating over jumps. And if I, yeah, if I do everything correctly, then from this, it is not so hard to see that then the total variation of the derivative, which I know I have basically almost a closed form of this, and I know that this integral is, it's a probability density, that is then bounded by exactly the measure of this mu. Yeah, I don't really want to. I don't really think that this can be understood at this point. But you can look into the paper why this would be the case. But the point is, we can have a bound on a property of the derivative easily, because we can just pull the derivative into this representation. And then what is left to do is basically find a function so that the TV norm of the derivative explodes, something like a cosine of n, and such that the classical Barron norm stays finite, which is the case for this function. So kappa is just some smooth cutoff function, which is obviously something you would have to just do the calculation. But in principle, for a function like this, you can then show, okay, this norm will go to infinity and this will not. And so basically from this, you can see that this thing is certainly not, continuously embedded in here. And if it's not embedded at all, it's a different question. But I mean, at least that's the first step. Okay, so that was kind of surprising, but it's also kind of a tangent because not really what we want to do right now. What I want to do is I want to now define functions that have jumps along curves, and these curves are Barron regular. So basically that means that they don't have a high variation. It's a higher dimensional form of bounded of the variation. So basically what I'm asking for is these jump curves, they should have a finite Fourier moment. And the way I define this is again locally, because okay, this is just something I define it locally. I just take a chart like here, and then I say, okay, in this chart, I want this to have a certain regularity, and this is the Barron regularity. Now we get this result. So f is of this form, and f has Barron class boundary. Then there exists a neural network, and this needs 4 layers. And it gets this, so for each measure mu, but don't be fooled, this measure needs to satisfy a certain number of properties, but the way I write it down, I would just put c equal to basically infinity, if basically as large as possible if mu doesn't satisfy these properties. So for certain measures, but these are almost all that you can think of, I have this bound. So the measure where this f is not equal to the neural network, that is bounded by a certain number, and this number decays like n, that's the number of neurons, to the minus alpha half. And alpha is a property, is a number that comes from the measure. So if this measure mu is your, let's say, your Lebesgue measure, then it's 1. then this alpha will be 1. So it will have actually the rate. We'll actually have the approximation rate n to the -1/2 in the L1 norm. And so it depends very mildly on the dimension, but not badly. So at least the rate doesn't. And this constant c, that depends on the measure. The constant m, the number m depends kind of on how well I can cover this jump curve. And I mean, having seen this result from before for smooth curves, I guess you're not very surprised that something like this holds. But seeing this like in isolation, I think it's kind of interesting, because you have a function that has arbitrarily high dimension and is not continuous. And it's also not like something bizarre like continue, only has a jump along a curve, but it has only has a jump along a line, but it has a jump along some kind of a curve, and the dimension is arbitrary and can still approximate it independent of the dimension with neural networks. That I would say is kind of cool. Now, to talk about how we can prove this, I mean, the proof is quite similar to before, so that's why now I talk about this A part, which is the localization step. So this is an idea that I first saw in a paper by Kaufman and Cloninger, which is basically to build these local bump functions. So rho is again the ReLU. I can construct a function like this by basically having first ramp, then I subtract a ramp, then I subtract another ramp, and then I try to make everything flat again. So with 4 ramps, I can build this local like indicator function approximation to an interval. And then I can just sum up d of them. So d is the dimension, subtract d and add 1, and then apply another ReLU. Then this thing is going to be 0 whenever one of these xi's is not in, well, 0, 1, the set where all of these should be larger than 0. And if it's really in the interior here, then this expression will be 1. So ReLU of it is also 1. So if you let n be sufficiently large, then this will approximate this characteristic function of a cube quite well. Okay. And from this, you can actually build something like a multiplication, but it's only a binary multiplication. So this is the function that I can approximate. Now this function here, where I just put, okay, omega can be any shifted or scaled cube of x plus y minus 1. This is the same as y times this characteristic function if y is 0 or 1. Yeah, because if it's 1, then this is exactly x, so chi of x. And if it's 0, then because this expression is always less than 1, this will always be 0. Okay, so but with this, if I now take a partition of unity, then I can localize really well by just composing with some of these functions. And that's how I localize here. So it really works with just 2 layers. I can localize certain functions. And then I have the same idea as before. I can locally write these functions as these as these horizon functions, where the gamma is now a function of Barron type. So it is like here. I'm not going to talk about the Heaviside again because we already did this in the earlier proof. And then because this is Barron regular, I mean, it has bounded free moment per assumption, I can approximate with this rate, 1/√n. Now let's go back, and you see the error that I make. Basically, I mean, the difference here is, so I do L infinity approximation, is 1/√n. And now I just have to find out what's the measure of that set. And that's where the kind of type of measure comes in. So for the Lebesgue measure, the measure of this is going to be of the order of 1/√n. But you could have a very, very angry measure that is only supported very closely to the jump, And then, of course, I cannot give you a really nice approximation rate with respect to a measure if the measure just tries to make things as bad as possible for me. So basically, if you think of a classification problem, and really all of the data points lie exactly on the on the classification boundary, then your world is pretty bad. But if they're kind of spread out, then it's much easier. And so here, this is how the kind of measure that we're trying to measure the error in plays a role. Okay, so one more thing. For cartoon functions, we had this nice thing that it was optimal, this rate. Now I can ask myself, is it optimal as well if I do the same thing with these Barron functions on functions, so functions that are Barron along curves? And yes, so I mean, this estimate is kind of elementary. So I can estimate the L1 norm between these characteristic functions by basically the L1 norm between the functions themselves. So what this means is that, I mean, this means that for a lower bound, things are quite nice, because if I can build something like an epsilon net for the space of Barron horizon functions, then this implies that I would also have something like an epsilon net for the set of Barron functions. Yeah, but these are functions that are horizon along Barron. But if I can approximate each of them quite well, then I can use this estimate to get some sort of a covering of these functions. But into the Barron space, which is a space that has one finite Fourier mode, I can put in another space, and this other space is some Bezoff space. I can just put in some Bezoff space. And for those, I had these covering bounds and so on and so forth. So this gives me a lower bound, which I cannot break through. And turns out that this is almost what we have as an upper bound. There's an additional one. There's an additional factor 1 over d in the exponent. So we're a little bit worse than the lower bound, but for d going to infinity, we match it reasonably closely. Okay. I want to summarize before, and after I summarize, I will talk a lot more about other things. I hope I can still do that. So basically, my point was: is a function with a jump hard per se, or is this hardness, does it come from just the type of jump? Is it only the regularity of the jump curve that is important here? And in most cases, for all the functions that we looked at of this form, it is actually so that you really, the approximation rate that you get for these singular functions, that's more or less that which you get for if the jump weren't there, in a sense. This is a very vague description, but really this jump is the regularity of the jump curve is the only really important ingredient. Is kind of how I'm trying to phrase this. And in particular, you see this with these piecewise Barron functions, where you have a high dimensional, arbitrarily high dimensional discontinuous function, and you get a dimension independent rate. And so coming back to the point from the dissertation of Candes, where he said, well, I mean, I can do this with just Fourier. Well, you can definitely not do this with Fourier. So high dimensional discontinuous definitely has a cursive dimension, while with the neural network approach, you don't see that. And that's kind of nice. So I want to talk about a couple of references. So this one is the paper by Barron, where most of this is kind of based on, and that has recently been like used a lot by also, especially by Ian Wojtowicz and others. And this paper I really want to mention because it kind of works on a similar problem. So they also work on classification problems. So it's almost like these kinds of functions that I was talking about. And they also show that you can get dimension independent rates for approximation of classification problems. They make it slightly different. They have a slightly different model. I would even say it's fundamentally different, because they say, okay, they want to have two classes and they have to be separated by a margin. And then you can always find functions that have different signs on these two sets. And this you can do without a cursive dimension. That's basically the ansatz in this paper. So it's less an approximation perspective, more can we solve classification problems, but we only care about signs. This is our paper, which hopefully is on arXiv tomorrow. Yeah, probably. And this is the one that I talked about at the very beginning, which is still in this classical point of view, where we have CK regular jumps, and we're trying to resolve those with networks. So before I stop, I also have a seminar series, as Emily said at the beginning. The next talk is tomorrow. It's every Wednesday, 12 p.m. Eastern time. This is the link to the webpage, and on that, when you follow that link, you could sign up to a mailing list. So it's basically the same format as for your seminar. And I wanted to have another slide that says thank you, but somehow that didn't work. So now you have a very blank page looking at you. But thanks.
Thank you very much, and for the interesting talk. And does anyone have any questions? Oh,